We continue our discussion on design of filters, and in this lecture we discuss the design of prototype equiripple or Chebyshev low pass filter, and then we will also discuss how the transformations are made from low pass to high pass, from low pass to band pass, and from low pass to band stop. Let us now consider the Chebyshev low pass filters. So, before we go into the design of the filters, prototype filters, let us first briefly discuss the Chebyshev polynomials. Nth order Chebyshev polynomial is a polynomial of degree n and denoted by T n x. Here we have T 1 x is equal to x, T 2 x is 2 x square minus 1, and we can calculate T n x from T n minus 1 x and T n minus 2 x. T n x is equal to 2 x T n minus 1 x minus T n minus 2 x. Now, the nature of variation of Chebyshev polynomials, some lower order Chebyshev polynomials are shown in this figure. For example, for n is equal to 1, it is a straight line. For n equal to 2, we find that this is the variation. For n is equal to 3, we can see that there is some oscillation. This is for n equal to 4, and therefore, we will find that the Chebyshev polynomial behavior is such that it will exhibit some oscillations in this region x is equal to minus 1 to x is equal to 1, and we can design equiripple low pass filter prototype using Chebyshev polynomials. Let us first consider the cutoff frequency omega c to be equal to 1 radian per second, and PLR is given by PLR is equal to 1 plus k square T n square omega. Now, since T n 0 is 0 for n odd and it is having a value of plus or minus 1 for n even, therefore, at omega equal to 0, we can write PLR is equal to 1 for n odd and 1 plus k square for n even. We have seen that T 2 x is given by 2 x square minus 1. Now, if we consider n equal to 2, then PLR will become 1 plus k square T 2 square omega, and if we substitute T 2 omega, it will be 1 plus k square 2 omega square minus 1 whole square. When expanded, this will become 1 plus k square 4 omega to the power 4 minus 4 omega square plus 1. Now, when we have a prototype network containing these two elements L and C, for this two element network, we have already seen that PLR expression can be written in this form, and from the Chebyshev polynomial the PLR expression is given by this. So, if we equate these two equations for omega equal to 0, then we get PLR is equal to 1 plus k square, and from here we get 1 plus 1 by 4 r 1 minus r whole square, and therefore 4 k square become 1 minus r divided by 4 r, and therefore r can be solved as r is equal to 1 plus 2 k square plus minus 2 k root 1 plus k square for even n, and here we have n equal to 2. Equating the two expressions for PLR, we get this equation the left hand side is from the Chebyshev polynomial and right hand side comes by deducing the expression for PLR for the circuit shown in the previous slide. Now, what we can do? We can equate the coefficients of omega square and omega to the power 4 from both sides. In that case, we get two equations. One is minus 4 k square is equal to r square c square plus l square minus 2 L C r square divided by 4 r. So, this is one equation we get, and another equation we get by equating the coefficients of omega to the power 4. So, we get 4 k square equal to L square r square c square divided by 4 r. Now, r value has already been calculated. We have already found out the expression for r, and therefore, we can solve for L and C from this set of equations. We should note that the value of r for n even is not unity, and so there will be an impedance mismatch if the load has unity impedance. This can be corrected with a quarter wavelength transformer or by using an additional filter element to make n odd. When n is odd, one can show that r is equal to 1. So, from these considerations, we can get the element values for equiripple low pass filter prototype. Prototypes we have already seen earlier, and we consider G naught equal to 1, omega c equal to 1. Now, here we also need to specify the passband ripple. So, this table is shown for 0.5 dB passband ripple, and we have seen from the behavior of the Chebyshev polynomial that Chebyshev functions, they exhibit ripple in the passband, and this calculation can be done for a specified value of the ripple. Now, we note that when n is equal to 1, G n plus 1 is 1. When n is equal to 3, we have G n plus 1 is again 1. So, for all odd n's, the load resistance, normalized load becomes unity, whereas for even values of n, the normalized load is not unity. So, once we design the prototype by using the values of G 1, G 2, G 3, and we can map them to the prototype circuits which we discussed earlier, and then we can carry out the impedance scaling as well as frequency scaling to get the actual cutoff frequency, and also the source impedance may be changed to the desired value of the source impedance. So, all these impedance and frequency scaling activities are to be performed to get a low pass filter with a desired cutoff frequency. The order of the filter once again will be determined by the specified value of the insertion loss at some frequency in the stop band of the filter. As we said that in the filter design process, we first need to find out the prototype filter, and once the prototype filter is designed, prototype low pass filter is designed, it can be transformed to the low pass filter with the actual cutoff frequency, or we can transform this low pass filter into a high pass filter with desired cutoff frequency, or to band pass filter with desired pass band, or a band stop filter with the specified stop band. So, let us see how these transformations work. The low pass prototype filter designs can be transformed to high pass, band pass or band stop, band reject response. Low pass to high pass transformation is achieved by frequency substitution. So, we have, this is the response of the prototype filter. We can see that the cutoff frequency is 1 and the PLR increases to the specified value at omega c equal to 1. Now, this PLR, where it has minimal cut at insertion loss at 0 is transformed to a high pass characteristics. So, here we see that insertion loss becomes very high below omega c, and above omega c the insertion loss decreases, and this type of a transformation can be achieved by substituting omega by minus omega c by omega, and when this transformation is applied, a series inductance j omega L k becomes minus j omega c by L k, and which essentially becomes 1 by j omega c k dash, where this c k dash is 1 by omega c L k. And similarly, j omega c k or L k dash is j omega c k is transformed to 1 by j omega L k dash, and therefore, this L k dash becomes 1 by omega c k. So, we can find that with this frequency substitution, we have already taken omega c into account. The cutoff frequency will be shifted to omega c, and then next we need to do the impedance scaling, because the source impedance is still unity, and then this C k dash becomes 1 by R naught omega c L k, and L k dash becomes R naught by omega c C k. So, this gives us the values of the L and C elements in the actual filter, which will have a source impedance of R naught and cutoff frequency omega c. Let us now consider the low pass to band pass and band stop transformation. So, the first transformation is a band pass transformation, where this low pass filter characteristics is mapped to a filter having a center frequency omega and pass band edges having frequencies omega 1 and omega 2. Similarly, if we go for band stop transformation, we get a filter where the center frequency of the rejected band is omega naught and the attenuation remains high for the band edges determined by omega 1 and omega 2. For performing low pass to band pass transformation, we need to substitute omega by omega naught divided by omega 2 minus omega 1 into omega by omega naught minus omega naught by omega, and this we can write 1 by delta omega by omega naught minus omega naught by omega, where we have delta equal to omega 2 minus omega 1 by omega, and we can get simpler equation if omega naught is chosen as a geometric mean of omega 1 and omega 2. Therefore, omega naught is root omega 1 omega 2. Similarly, when we perform band stop transformation, so when this band pass transformation is applied, a series inductor L k is transformed to a series L C circuit, and the values of this L and C parameters are given by this. L k dash is L k by delta omega and C k dash becomes delta by omega naught L k. And a shunt capacitor C k is transformed to a shunt L C circuits, and the element values are given by these expressions. When we go for a band stop transformation, so for a low pass to band stop transformation, we substitute omega by delta omega by omega naught minus omega naught by omega raised to the power minus 1. So, essentially it is the reciprocal of the band pass transformation, and when this frequency transformation is applied, a series inductor is transformed to a parallel L C circuit, and we can find out the values of this parallel L C circuit L and C from the given L k, delta and omega naught. Similarly, we can find out C k dash is equal to 1 by omega naught delta L k, and also the shunt capacitors are transformed to series L C circuit, and the values of these series L C circuit elements L and C are determined from the original shunt capacitor C k, and the relations are as shown. So, in summary, if we summarize the transformations, we have in the low pass circuit L and C, when we make low pass to high pass transformation, this L is transformed to C and C is transformed to L. When we go for band pass transformation, this element L is now transformed to a series L C circuit, and this C is transformed to a parallel L C circuit, and when we go for band stop transformation, this L is transformed to a parallel L C circuit, whereas C is transformed to a series L C circuit. You can see that the values of this series and parallel circuit elements can be found out in terms of the original circuit element. For example, here this L and C both are related to original L, and delta we have defined it to be omega 2 minus omega 1 divided by omega naught, and omega naught we have defined root omega 2 into omega 1. So, we can calculate the component values of these transform circuits, and therefore, when in the prototype we will have to substitute them by respective combination of elements. We have only done the frequency transformation. The impedance scaling also needs to be done for transforming the source impedance. Impedance scaling also need to be done to complete the procedure. Let us now very briefly discuss some of the issues related to the filter implementation, because so far in our discussion we have considered lumped elements L and C. Now, these elements as lumped element circuits can be used. So, these elements as lumped components can be used only at the lower microwave frequencies. As we go to higher microwave frequencies, it becomes very difficult to realize these capacitors and inductors in the lumped form, and often these are realized in the form of transmission line sections. So, lumped element design discussed so far works well at lower frequencies. At higher RF frequencies, lumped element inductor and capacitors are generally available for limited range of values. At higher microwave frequencies, such elements are difficult to implement. So, we need to use distributed element such as stubs, which often used to approximate the lumped elements, and conversion of lumped element to equivalent transmission line sections can be done using Richards transformation. Moreover, when we connect these elements in a microwave circuit, the spacing between the filter elements are also to be considered at the microwave frequencies, and Kuroda's identities are used to physically separate filter elements by various transmission line sections. So, without affecting the response, we can have these elements connected together by suitable transmission line sections. In this module, we have discussed the various power dividers. We have also seen the design issues involved. We have also seen the different issues involved in the design of microwave frequency filters. We have discussed to somewhat detail the insertion loss method of filter design and how we can start with a prototype low pass filter design, and later on we can transform it into a low pass filter of desired cutoff frequency or to a high pass or to a band pass or to a band stop filter. In the next module, we will start with the semiconductor devices. We will discuss the microwave transistors, the BJTs and field effect transistors. We will also discuss some of the important microwave frequency diodes such as Schottky diodes, PIN diodes and their application. We will also discuss the devices based on transferred electron effect, the GaN devices.